Hi everyone, my name is Ori Ossmy. I'm from New York University, and I'm going to present my behavioral approach to the development of common sense. Studying the development of common sense can inform researchers from many disciplines interested in systems that have common sense, from psychologists and neuroscientists up to computer scientists and roboticists. Traditionally, developmental researchers study common sense based on looking time studies, in which they assess what infants know about the world based on group differences in looking time. In these studies, researchers infer what infants know about specific objects, agents, events, or properties by displaying those on a flat screen and scoring how long infants look at each display. However, human common sense in real life is evaluated by what humans do. When we say that a behavior makes sense, we mean that the observed actions make sense. Therefore, when computer scientists and roboticists are interested in machine common sense, they are interested in a machine that acts with common sense. Looking time ignores the behavioral richness of what infants do. The looking time approach does not inform on developmental changes in real-time mechanisms underlying common sense behavior, and neglect questions like what goes wrong when infants and children act in a way that does not make sense to adults, or how does experience over development change that. Moreover, the looking time approach is limited in explaining individual differences in common sense. This is crucial for researchers who are interested in machine common sense because when implementing common sense in a machine, computer scientists and roboticists observed a wide range of active behaviors by the machine that looking time by itself cannot explain. Our behavioral approach to common sense is focused on what infants and children see and do. We examine changes in how children solve problems. Let me give you an example of one of our tool use studies. When adults use a hammer and the handle of the hammer points to their dominant hand, a habitual overhand grip leads them to use the hammer in a way that makes sense. But when the environment changes, and the handle of the hammer points to their non-dominant hand, adults need to change the habitual grip to an underhand grip that will lead to a hammering action that makes sense. This underhand grip demonstrates a common sense behavior. Infants and young children do not show this kind of common sense behavior. Children use the hammer in an habitual way regardless of whether it is a dominant or non-dominant hand condition. In the non-dominant condition, a habitual grip leads to a weird hammering that won't make sense to adults. This figure shows tremendous inter and intra-individual variability in children's common sense behavior. Each column is one participant, and the turquoise color indicates the percent of non-dominant trials when participants used an underhand grip that reflects common sense behavior. Adults use an adaptive underhand grip all the time, but children vary. Some children display common sense like adults. Those children are the adaptive solvers. They use the underhand grip more than 90% of the time like adults. Some children did not show common sense. Those are non-adaptive solvers, and they use the underhand grip less than 85% of the time. The non-adaptive child solvers were younger than the adaptive solvers, indicating developmental changes in common sense. What drives children to common sense behaviors? In our behavioral approach, we investigate the interplay between perceptual, cognitive, and motor processes that drives developmental changes in common sense. We combine perspectives and methods from developmental psychology, AI, computer science, neuroscience, and movement science. I will start by showing how common sense behavior depends on a real-time cascade that starts with perception to gather information, then processing the perceptual information in the brain, and finally translating the processed information into action. To examine the real-time cascade and its relation to developmental changes in common sense, we integrated multiple technologies and came up with the new hammering studies where adults and children sat on a chair wearing EEG, eye tracking, and motion tracking. All of them synchronized with the robotic screen, which allowed us to control the exact times at the resolution of milliseconds when they perceived the hammer. The children and adults sat still for a few seconds before the screen was open, and they were aimed to grasp the tool, the hammer, and hammer the peg. Using the head-mounted eye tracker, we examined what visual information was gathered and when. We got the location of the participant's fixation, just like this video on the left. From that fixation location, we created looking video that contained the visual information each participant acquired in each trial. Then we aligned all the frames from all participants in all trials such that the hammer and the peg will be in the center. And we examined the probability of each group to look at specific location of the scene at specific time. We focused only on the time from screen opening to movement onset. This looking probability video shows that adults look at the hammer orientation immediately. Adaptive child solvers also look at the hammer orientation relatively early. But the non-adaptive child solvers did not. This heat map shows where each group looked on average relative to the hammer and the peg. Non-adaptive child solvers who do not display common sense don't focus specifically on the tool or the goal. They look all around. Using the EEG, we measured the second component of the cascade, information processing. These graphs show the difference in readiness potential, the neural correlate of action planning, between the dominant and non-dominant condition. 0 in the graph is participants' movement onset. Adults show an early difference. Adaptive child solvers show a later difference, and non-adaptive solvers show no difference at all. Finally, motion tracking shows the last component of the cascade, the exact movement performed. Similar to the neural components, the difference in movement trajectories between the dominant and non-dominant condition begins earlier in adults than adaptive child solvers and never differentiates in the non-adaptive child solvers. Developmental shifts in the onset of the real-time cascade and in the timing of its components drives children to a common sense behavior. Adults and adaptive child solvers fixated sooner, showed earlier neural differentiation than adaptive children. Non-adaptive children showed no neural difference at all. Adults had earlier movement onset and earlier differentiation of their movement trajectory compared to adaptive children. Non-adaptive children showed no movement differentiation at all. This earlier cascade led to an earlier and adaptive hammering. Altogether, we learned that if looking starts too late or the neural processing is too slow, children have already started a movement that eventually ends with an initial grip that does not make sense. Common sense behavior depends on a competition between perception and action. These findings raise a related developmental question. How does experience improve common sense behavior? One option, from a nativist point of view, is that infants begin with an innate prescribed solution to a problem, and experience elaborates on this solution to make sense in different situations. Alternatively, from an emergentist point of view, infants begin by generating a variety of solutions, and experience teaches them to assemble the appropriate solutions for the specific situation. For example, how do pre-walking infants solve the problem of cruising between two supporting handrails with changing distance? We use computer vision to translate infants' arm and leg movements into a time series that reflects their coordination patterns. You see the time series below. Then we evaluated the similarity between each pair of trials across infants and distances. The coordination patterns in top two time series are more similar than the coordination pattern in the bottom time series. This procedure yielded a similarity matrix. We used unsupervised clustering to identify strategies children use to cruise between the two handrails. On the right, you can see the similarity matrix ordered according to clusters. On the left, all the trials represented in the similarity space after multi-dimensional scaling. We found 8 clusters representing 8 strategies. Some strategies make sense for large, challenging distances. For example, in strategy number 1, infants take a few steps between handrails and then stretch their arms to the other side. Here is how it looks like. Where the ratio between the gap size and the infant body is high, it makes sense to some advantage by making few steps toward the center of the gap and then lean forward to get to the other side. Using this strategy when the distance is small does not make sense, because when the distance is small, infants can just reach with their hand to the other handrail without the need to stretch their legs first. Other strategies make more sense when the distance is small. For example, in strategy number 8, infants cross the gap by moving their arms and legs in an antiphase pattern. And this is how it looks like. When the distance is small, this strategy is very efficient. However, for large gap sizes, it does not make sense to use this strategy because it limits infants' reaching distance. We looked at the likelihood for experienced and novice cruisers to use specific strategies in specific body-environment relations. We assessed body-environment relations as the ratio between the distance between the handrails and the infant's arm span. Experienced and novice cruisers use strategies differently. The diagonals in this graph shows whether this strategy makes sense in a specific ratio between infant's arm span and the handrail distance. High ratio is a challenging, whereas low ratio is easy. Both experienced and novice cruisers used all the strategies, but only experienced infants selected the appropriate strategy for the right arm distance ratio. Experienced cruisers also experience also affected how many strategies infants use at each distance. Replacing strategies where the distance remains the same does not make sense. Novice cruisers use multiple strategies inconsistently, whereas experienced cruisers change strategies only when it's necessary. These beneficial effects of experience were specific to cruising. Experience with crawling, another skill that involves coordination of 4 limbs, did not improve cruising. Altogether, our findings support the emergentist view. Infants begin with a variety of solutions, and with experience, they learn to assemble a strategy that makes sense in the specific body-environment relations. Because infants have a variable experience when they learn to cruise, our approach suggests that variable experience can lead to a common sense behavior. In the final part of my talk, I want to give an example of how infants' experience and behavior can inform common sense behavior in robots. To that end, I use walking infants and soccer-playing robots. Much like humans, for robots, functional movement in a realistic environment requires common sense. One example of an assessment of successful common sense in robots is robot soccer competitions, Robocup. Why soccer? Because soccer-playing robots must move adaptively in a dynamic environment and interact with other agents. We taught simulated robots to play soccer using real infant behavior. From day one, infant walking experience is extremely variable and includes frequent starts and stops, curved paths, and steps in all directions. We examine whether this variety is beneficial for developing common sense. We first observed infants in free play. Using computer vision, we located them in the scene. We tracked their body movements in each video frame, and we got infants full walking paths. In the first soccer tournament, we asked whether training robots on real infant paths would be as good or better than training robots on non-variable paths, such as straight lines, circles, and squares. The short answer is that infants win. Across 1,000 simulated matches between each pair of teams, the team that was trained on infant paths outscored all other teams and won most of the games. In the second tournament, we tested variety in infant paths. We clustered 75 infant paths into five teams based on the variability of their path shape, changes in direction, bout length, and numbers of starts and stops. The purple team was most variable on all measures. Within infants, variety wins. The purple team that was trained on the most variable infant walking path outscored all other teams and consistently beat them. These findings suggest that variability promotes functional behavior that reflects common sense behavior. To conclude, infants provide rich behaviors that can be used by computer scientists to develop human-like common sense. Studying infants and children during problem solving reveals how the interplay between real-time mechanisms lead to an emergence of common sense. Finally, all the examples I showed you today use concepts and methods from AI to address developmental questions. Therefore, AI provides a fruitful avenue for testing hypotheses about infant development. Reciprocally, observations of infant behavior may inform research on AI. Both fields should work together more closely. I want to thank my wonderful collaborators and the various funders. And thank you for your time.